and I'll for all the speakers, at about 12 minutes, I'll turn on my camera, and then you can use that as a hint to work towards concluding, please. And otherwise, I guess I'll pass it to Susan, who will be doing the introductions.
Okay, I'd like to welcome everybody to the second part of our session. And I would like to thank the co-conveners who ran it this morning when it was before breakfast time for us on the West Coast. And we have 6 speakers this afternoon, and I think there's some themes running through these talks, so I think it's going to be a very nice session. Our first talk today is by Rebecca Pierce, who will talk about nitric oxide production in the global ocean, control by nitrification and denitrification pathways. Take it away, Becca.
Thanks so much, Susan. Just start sharing my screen here. All right. So hello, everybody. My name is Rebecca Pierce, and I'll be discussing nitrous oxide production in the global ocean, controlled by nitrification and denitrification pathways. This is a collaborative effort between myself, Dr. Jim Christian, and Dr. Roberta Hom, and it's done through the University of Victoria, MEOPAR, and Fisheries and Oceans Canada. So to start with, what is nitrous oxide and why is it even important in the first place? Well, it's our 3rd most abundant greenhouse gas. It has a global warming potential that's almost 300 times higher than carbon dioxide, and it's currently the single most important ozone depleting emission, and atmospheric concentrations are rapidly increasing, mostly due to increased use of agricultural fertilizers. Ocean production of nitrous oxide comprises a significant portion of these emissions, but it's also poorly constrained at anywhere between 10 to 53% of the total. As climate change progresses, global climate models are projecting ocean deoxygenation, and this will influence most of the nitrous oxide production pathways. So to understand these production pathways, we need to take a look at the nitrogen cycle. Luckily, we don't need to focus on the full complexity of this. We really only need 3 or 4 main processes. So to start with, at the top there, we have remineralization, where organic matter is converted into ammonium. This can happen either in the oxic ocean or in suboxic waters, such as in oxygen minimum zones. Then we have nitrification on the left, where ammonium is oxidized to either nitrate or nitrous oxide, and this only occurs in oxygenated waters. Denitrification, on the other hand, only occurs in suboxic waters, and it can either produce nitrous oxide by reducing nitrate, or at even lower oxygen concentrations, it can consume nitrous oxide by reducing it further into elemental nitrogen. So to show these reaction processes, we've created a computer model that is a chemostat. A chemostat is essentially what you're looking at here. It's a virtual laboratory. So if we had a beaker that we fed our inputs into, had our known reactions occurring with our outputs that we then fed back into the system, we can generate steady state conditions that allows us to determine the rates of each of these reaction pathways. We can then apply this to a 3D framework by running the experiment at every point in a 2x2 latitude-longitude grid over multiple depth layers. This is what allows us to examine the effects on production due to global variation in environmental conditions, especially that of oxygen. So we can use this model to answer a few specific research questions. For one, how much nitrous oxide production occurs in the oxic waters versus the suboxic waters? What are the main controls on nitrous oxide production by nitrification, and what are they by denitrification? And what are the biggest uncertainties when we're parameterizing the system? How strongly do these uncertainties actually affect our net production of nitrous oxide? Starting with the first question, how much nitrous oxide is produced in the oxic ocean versus the suboxic ocean? If we look at the figure on the right, it's almost completely uniform because most of the ocean is oxygenated. So we'll only see nitrification happening here, and it tends to happen at smaller rate processes. But if we take the same figure and we apply it to a logarithmic scale, we can see that we actually do have more variation even in the oxic waters. And we also have these hotspots of production. These are where denitrification is occurring in oxygen minimum zones. So we can take a better look at the difference between these 2 locations. One which is in that North Pacific oxygen minimum zone, and one which is in the oxygenated waters of the North Atlantic. This first one is the oxic waters of the North Atlantic. So starting at the left, the oxygen concentration, you can see it doesn't vary a whole lot, and it never really reaches close to zero. This means that all of the production is from nitrification, and it occurs at lower rates than we'd expect from that of denitrification. You can see on the right there that both production and consumption by denitrification are zero. This is because no denitrification occurs in the oxic ocean. It only occurs at lower oxygen concentrations. So in the North Pacific oxygen minimum zone, we can see that oxygen does reach these low concentrations, and we start to see spikes of very high production rates. We still have nitrification occurring. We just have a lot more of denitrification production, and we also have some small amount of denitrification consumption. So when we have oxygen minimum zones, this means that production from denitrification is dominant and is much stronger than we have from nitrification. Looking a little bit more into nitrification, we need to ask ourselves how oxygen affects the yield of nitrous oxide instead of nitrate from this process. So we can represent this with the equation shown below, but the parameterizations of those constants A and B tend to vary. These are shown on the figure on the right, and you can see that as we're at higher concentrations of oxygen, we have very low yields of nitrous oxide, but they tend to increase as we decrease in our oxygen concentrations. So while nitrification is an oxic process, at low oxygen, it has very high yields of nitrous oxide. If we apply this in the scheme of our 3D model, we can take a look at the production from each of these processes as well as the net production. So the nitrification is that second bar there, and you can see that we do see some variation from different parameterizations of the yield, but it's not quite a lot. And since the net production tends to be dominated by denitrification, it doesn't affect the net production in a huge amount. However, it does show how it's affecting how much nitrous oxide is produced from the nitrification pathways, and all of these parameterizations have been used in literature before. If we take a look more into the denitrification, we need to ask ourselves, at what oxygen concentration does it begin and when does it end? We can also describe denitrification as suboxic remineralization. So the proportion of suboxic to oxic remineralization can be represented by our equation below called omega. The oxygen thresholds that have been reported through literature can range anywhere between 3 to 20 micromoles per liter. This is essentially showing how we define our volumes of suboxic waters. So as we increase from 3 to 6 to 10 to 20, you can see that our hotspots are expanding because we're essentially saying that denitrification can now occur at much larger volumes of water. Taking this into our 3D scheme, you can see that there's actually a massive amount of variation, both between the production from denitrification and from net production. If we increase all the way up to 20 micromoles per liter, we can actually get up to 65 teragrams of nitrogen per year from our model, which is an exorbitant amount, but it really shows how much variation we can get just from changing this one term. This means that oxygen threshold has a very substantial effect on how much nitrous oxide is produced by denitrification, since it's expanding how we define our volume of those suboxic waters. Another question to ask for denitrification is, how exactly does it get inhibited at that oxygen threshold? So going back to that omega equation, our exponent C can range from 0.3, 0.6, 1, 3, or 6. And you can see from the figure on the right that it affects the shape of that curve of the fraction of oxic or suboxic respiration. Again, taking this into our 3D model perspective, this is showing how our denitrification production as well as the net production are quite heavily affected by this, though nowhere near to the degree that of the oxygen threshold had. So our exponent C is really reflecting this nitrous oxide produced by denitrification, since it shows how it changes how quickly the fraction of suboxic mineralization increases as we decrease with oxygen. Another thing to consider is what we're inputting into our models. So the input of gridded data products can be another source of uncertainty here. Especially when it comes to oxygen, it's known that they can be quite inaccurate at the low oxygen concentrations that we really need for this model. So on the left, we have the World Ocean Atlas data from 2018. And you can see that it does reach lower concentrations of oxygen, we don't actually see any of the high production rates from denitrification because it doesn't cross that threshold. If we take the same data and apply the Bianchi correction method from 2012, you see that we can actually reach some of the lower concentrations and see a little bit of that denitrification showing up. But in 2021, Krasinski and Babin came up with a new oxygen gridding scheme that is much different from both of them and shows a lot more accuracy in the low oxygen ranges. These are all in the same location in the North Pacific oxygen minimum zone, and you can see that nitrous oxide production rates vary widely. This is because we really only have a small range of oxygen concentrations where denitrification occurs. So if our oxygen threshold is 6 micromoles of oxygen per liter, then we really need the gridded data products to accurately reflect this. Otherwise, we won't see any denitrification production. Another way to lose some of this low oxygen data is when we're converting the data products to 3D and 4D grids, because at that point, sometimes we can smear them out by spatial and temporal averaging. So some of the conclusions that we have so far from this model, first off, it's that the parameterization of the nitrous oxide yield from nitrification does have a significant effect on global net nitrous oxide production, anywhere between 0.5 to 6 teragrams of nitrogen per year. The exponent C in our omega equation mostly only affects nitrous oxide production by denitrification and to a slightly smaller degree of around 1 to 3.5 teragrams of nitrogen per year. But it's also not really defined anywhere in the literature. We also found that the input of our gridded data products to the model will also carry uncertainties, especially when these low oxygen concentrations are underreported or if they're averaged out. Finally, out of all of these depicted uncertainties, the oxygen concentration where denitrification production begins has the largest control on global nitrous oxide production rates. They can affect them by ranging anywhere from 5 to 65 teragrams nitrogen per year. And these literature estimates really do have a wide range between 3 and 20 micromoles of oxygen per liter. As climate change progresses, we do have these global climate models projecting both global deoxygenation of waters and expansion of those oxygen minimum zones. With less oxygen in the water, this means we could have increased nitrous oxide production, especially from those oxygen minimum zone hotspots where denitrification can occur. It really highlights how we need to improve our understanding of nitrous oxide and nitrogen cycling systems so that we can prepare for an altered future. This model itself is still a work in progress, but we do need more models that are collaborating more with observational scientists. We're just hoping that this model will help us narrow down what the uncertainties we most need to study next will be. Thanks to everybody for listening, and I hope we have a bit of time for questions and comments.
Great, thank you very much for a very interesting presentation. We have about 3 minutes. Okay, I already see a first question. Dave Greenberg, would you like to go first?
Hi, pardon if this is a physical oceanographer's misunderstanding of what chemical oceanography is all about, but if I understand it correctly, chemostat is the principal tool you're using. Is that and what you're saying is that if you don't get good inputs, you don't get good outputs. But I'm wondering about chemostat itself. If you have exact inputs, do you trust exactly what comes out of it, or is it are there a lot of approximations gone into chemostat as well, or do I have that wrong?
No, there are definitely some approximations that are going into it. One thing that we really had to focus on is the fact that we can't use any outputs of concentrations, for example. We really have to focus on the rates. Because you're right, as we're using this steady state conditions through the chemostat, it's going to affect, our input is going to affect the output, and we can't take everything for granted. But we do know that there are recordings of, for example, nitrification production at those low oxygen concentrations, and then those low oxygen concentrations don't get reflected in the gridded data products. So there are some uncertainties like that that we know are truly inaccurate. Sorry for the oxymoron.
Okay, so ballparky, if you have accurate inputs, what kind of variation do you think you might see if you don't have a steady state?
If I don't have a steady state?
Yeah.
Without the steady state, we can't really calculate for the rates themselves. So we have tried using just a time-based model that doesn't have steady state conditions. But at that point, we're only producing concentrations that wouldn't truly be accurate rather than the rates themselves.
Thank you.
Yeah, thanks for the question.
Great, thanks for the question. Any other questions from anyone? If not, feel free to put them in the chat or contact Becca directly with those. If not, I think it's perfect timing for moving on to the next speaker. Thank you.
Thank you.
You're muted, Susan.
Sorry about that rookie mistake. Our next presentation is going to be given by Eliette Chanel, who's going to talk on the assessment of sea ice with NEMO 4.2 SI3 coupled model for operational purpose. Go ahead.
Okay. Can you see my slide?
Yes, that's good. And
That's
speak up
great.
a little bit.
Okay. And can you hear me correctly now?
Yes.
Okay, perfect. So hello, my name is Eliette Chanel, and I'm a PhD student working at Mercator Océan in collaboration with the Center of Spatial Studies from France. And I'm in Toulouse, France right now. I'm going to be talking to you about the new NEMO 4.2 and SI3 coupled model, a new configuration that I've been using. And here you can find the outline of my talk. After describing the models, I will compare the results of the previous configuration, NEMO 3.6 and LIM3, to the results of the new configuration, NEMO 4.2 and SI3, in terms of sea ice variables and in both hemispheres. I will then be presenting briefly some sensitivity experiments that I did on this configuration. On this slide, I present to you the two models that I used. The global ocean model NEMO is coupled to the sea ice model, LIM3. No, sorry, it's coupled to the sea ice model. And before we used the NEMO version 3.6 with the sea ice model LIM3. And since March, we are now using NEMO version 4.2 and SI3. The new features of the sea ice model are listed in this blue box. And the new functionalities of the NEMO related to sea ice are in this other box. We did not put on all the new functionalities in my configuration because we wanted to stay close to our previous simulation setup. We still activated some interesting new physical processes, such as sea ice lateral melting and landfast ice modelization, and also some numerical features, such as the adaptive elastic viscous plastic rheology, so adaptive EVP, that helps us speed up the computational time. Moving on to the next slide. Our objective with this work was to minimize biases in sea ice states because we plan to assimilate sea ice thickness products. The simulation is performed on the global grid with a 1/4 of a degree resolution. And the atmospheric forcing is the ERA 5 reanalysis. Our simulations run over a 10-year period from 2010 to 2020. We analyze these results with 3 variables: sea ice concentration, sea ice thickness, and thaw thickness. A series of sensitivity experiments were performed with parameters that can influence greatly sea ice stage. So the snow albedo, the ice albedos, and the thermal conductivity of the snow. I will now present to you a glimpse of our results. On this slide, you can see the sea ice concentration of the simulation in the Arctic. The first line here represents the state of the sea ice at the end of winter in March, and the second line is the state of the sea ice at the end of summer in September. The model is compared to the OSISAF satellite data, which is represented on the first column. The second column shows biases of the previous model, NEMO 3.6, with LIM3. And the last column is the biases of the new model, NEMO 4.2 and SI3. Both models seem to be in a general good agreement with the observations. However, we observe a bit too much ice on the east of Greenland for both models at the end of winter. In summer, the regional biases differ from one model to another. With NEMO 4.2 and SI3, the map shows here an underestimation of the sea ice cover in the western basin, and an overestimation of the sea ice cover in the eastern basin. Let's now switch to another sea ice variable. The ice thickness represented on this slide in the Arctic is compared to the satellite Cros Sea-ice data. The first diagram here shows the evolution of the mean sea ice thickness. In winter, both models, so the new SIQ model is in orange and the old one, the previous one, sorry, limb 3 is in dashed blue line. In winter, you can see that they are quite in agreement with the observation. The observation are the green crosses. You can see that in summer, the new SIQ model has a lot less sea ice thickness than the previous model. On the right side of the slide, these are maps and PDF, probability density functions, of the March monthly mean of sea ice thickness, so at the end of winter. It shows that the PDF of the model are in quite good agreement, with same as previously. In orange, the new SIQ model, and in dashed blue line, the NIMO 3.6 and limb 3 previous model. In green, you can see the observation, satellite observation. On the maps, the biases of the two models here are quite similar. The ice is not thick enough in the north of Canada compared to the accumulation that we can observe with a satellite. In situ observations can also be used to assess the capacities of the model. So here I present a comparison with the IceBridge QL campaign measurements. The ice thickness from the simulations show a completely different diagram between limb 3 on the left and SIQ on the right. Limb 3 overestimates the ice thickness, while SIQ tends to underestimate it when compared to this dataset particularly. Moving on to analyzing the snow thickness. Our comparison data is a snow KU product that is computed with measurements from both satellites, Cros Sea-ice and Antarctica. This shows on the right side a temporal evolution of the snow mean thickness, and on the right side, plots of the March monthly mean. Both models present here very similar results. They both overestimate the snow depth compared to the satellite measurements at the end of winter. On the maps, you can see that this positive bias is quite homogeneous around all the Arctic, which means that the spatial distribution of the models is in good agreement with the observations of the satellite. The PDF of the models shows also an overestimation of the snow thickness with the models here and the satellite being the green curve here. Now, so after analyzing the simulation results in the north, let us observe it in the south. These maps here present the sea ice concentration in Antarctica. The first line is at the end of winter in September time, and the second line at the end of summer in March. In September, the sea ice extent is overestimated by both models. The new SIQ model is even more biased than the previous limb 3 model. In summer, however, both models have a completely different sea ice field. Limb 3 shows an important lack of sea ice all around Antarctica. And SIQ shows a large overestimation of sea ice concentration. But the model still is not able to keep sea ice along the eastern part of the coastline here. How about sea ice thickness in Antarctica? We have a paradox in Antarctica with both our models. As we just saw, the sea ice extent is higher than the observation, but the thickness here is lower. On this graph, which is a temporal evolution of the mean sea thickness, you can see that the new SIQ model in orange has a thicker ice than the previous limb 3 model. However, it is still not able to reach most of the observations from the satellite. The maps and PDF here for September monthly mean also show this bias of this negative bias of sea ice thickness. And in the PDF, you can also see that the sea ice thickness is not distributed equally for the models and the satellites. If the sea ice is too thin in Antarctica, the snow cover, however, is too thick. LIM3, the previous model, overestimated a little the snow thickness, but the new ADCP model here presents a large increase in snow depth compared to it. The maps and PDF of the September monthly mean emphasize these results. There is too much snow in Antarctica with our configuration SIQ. And on the PDF probability density function, you can see it also, like the orange line is really on the side compared to the other two PDF. After having observed the results of this new NEMO 4.2 and SIQ model, I will now present a short overview of the sensitivity experiments performed with this configuration. So the purpose of this sensitivity experiments was to correct the modeled sea ice. We want to reduce biases and sea ice thickness, mainly because our goal is to assimilate radar freeboard data with this configuration. We tested 3 categories of parameters: snow albedo, sea ice albedo, and snow thermal conductivity. The values were reduced according to values found in the literature, and the results are expressed in terms of percentage of loss for the different sea ice variables: sea ice concentration, sea ice thickness, and snow thickness. The results are presented in the Arctic and in Antarctica. The tests show an important impact of sea ice albedo and snow conductivity in the modelization of sea ice thickness and snow thickness in both hemispheres. Snow conductivity, however, has the largest impact in Antarctica, in green, the green bars. Sea ice concentration is not as sensible to these parameters as the other 3. And yeah, so the sea ice albedo has a great impact too. The albedo in the model are expressed in terms of dry and melted sea ice albedo. That's why you have 2 initial values for sea ice and snow albedos for the dry and melted one. I will now summarize the presentation. As we've seen, there are significant differences between the 2 model configuration, NEMO 3.6 and LIM3, and NEMO 4.2 and SIQ. In the Arctic, with sea ice thickness, first of all, as we could see with the in-situ measurements, but more impressively in Antarctica, for the sea ice and snow variables. This study emphasizes the difficulties of adjusting one set of parameters to represent both hemispheres. And the sensitivity experiments showed a great impact of the sea ice albedo and the snow conductivities. However, we would like to continue our sensitivity test with other variables that can have a big impact on our sea ice field. For example, we were thinking that maybe the fraction of snow falling into the sea, which is a parameter of the model, could help us reduce the biases that we noticed. We will also develop the study with a validation of the sea ice dynamics variable, such as the ice velocity, to have a more complete analysis of the new configuration. This configuration will be used to develop a data assimilation system as a part of my PhD. My PhD, which aims at assimilating radar freeboard data and snow measurements to constrain the sea ice thickness. Thank you for listening, and please don't hesitate to ask if you have any questions.
Thank you again for another very interesting presentation. We have a couple of questions in the chat. Hopefully we'll have time for both. Yo-Yu, you were first, if you'd like to ask your question.
Yeah, my question is in the chat. So how many level in the vertical? You use a 50 level or 75 level setup for this one?
So we can repeat?
He's asking how many levels do you have in the vertical, and do you have the same vertical setup for all experiments?
Yes, in the ocean model, we have 75 vertical levels, and it is the same number for both experiments.
Okay. Yeah. Okay. Thanks. Yeah.
Frederick, would you like to ask your question?
Thank you, Paul. Alia, I think you mentioned in your conclusion that, so I suppose you haven't tried the blowing snow scheme that is available in ICQ. Is that correct?
That's correct. I haven't tried it yet. That
Okay.
should be one of my next parameter maybe to try and.
And I guess since I have the floor, did I understand correctly that you can actually tune the albedo separately for the south hemisphere and north hemisphere? Is that correct?
No, the albedos are the same for both hemispheres, and that's why we experience little difficulties in having a correct sea-ice phase in both hemispheres. Yeah.
So should we have separate sets actually?
It would be like the physics is not the same in both hemispheres, and so yeah, I guess it would make sense to have separate configuration, not configuration, but parameters. However, like yeah, it would be a good test. There is Gilles,
Michael.
This is director,
Michael
who is also
that would be
answering if you have more specific questions.
So you asked Michael's question right for him, Frederick. Thank you both very much. And then I think we should move on to the next speaker now. Thank you.
Thank you.
Our next speaker is Andy Lin, who is going to talk to us about
You're mute again, Susan.
I'm struggling here. Okay, Andy Lin, who's going to talk to us about, come back. Andy Lin is going to talk to you about development of a relocatable ocean model for the west coast of Canada.
And just before you start, Andy, I'll mention, I think there's an issue in the program. Because it lists you with 25 minutes, but I believe you have a normal 15-minute presentation. So I hope that's not a problem.
Not a problem. Yeah, I only prepare 15 minutes.
That's what we were hoping. Thank you.
Thank you. Yeah. Hi. Good afternoon. I'm Andy Lin. Co-authors are Mike, Maxime, Hawk, Roy, D. We are from iOS DFO, Sydney, BC. So this research was under Oceans Protection Plan, Functional Area 5. I'd like to thank Functional Areas 1 and 2 modelers and Oceanography Working Group members for their support as well. We have the workflow and how we implemented the system. Then we're going to go through 2 cases, Bligh Island and the Prince Rupert areas. The last section is the summary and a few thoughts. So first one is the workflow as shown here. It's a relocatable modeling or a system and should be deployed quickly or set up automatically when there's an emergency in any area if you have a parent model domain. So we start from the definition of the domain and the resolution in both horizontal and the vertical. Then look at the bathymetry and the database and the coastlines. Automatically generated the grid files, including the mesh mask and the bathymetry. On the other hand, we're going to look at the parent model. For this study, we use the Southwest Coastal Ice Ocean Prediction System for the West Coast. It will generate the initial condition and the open boundary conditions. On the surface, we use the HRDPS from ECCC to generate the winds, pressure, and surface flux. So those are forcing files. Another one is the control file. We need the configuration and the parameters. So we use functional areas 1 and 2 pod models. I think Mike and Rachel, they're going to present in the next for those details. So it will automatically find the similar resolution and use those as a referential model to generate the control files. So all those input files should be automatically generated. So at least the tools we have either developed or incorporated from other sources. So we have Surf, Nemo platform for the grid file. We have grid tools, which can dig channels and fill up lakes. We also have BDY tools for initial and open boundary conditions, weight tools for the surface forcing. The goal here is to automatically run system with a minimum human intervention, but as we found out, a better understanding of the regional and the local oceanography is going to minimize the iteration and affecting, it's important how you define the domain and that select the resolution as well. So next, I'm gonna go through the two cases. The first one is the Bligh Island one. The right panel is showing the bathymetry database that we used. It's called Canada West Coast Topobathymetric Digital Elevation Model. So you just define the box here as showing on the left panel. It's about 300 times 200 grid. The horizontal resolution for Bligh Island area is about 150 meter. In the vertical, we have 50 layers. The resolution ranges from 1.1 to 10.8 meters. There are actually two model runs, but due to the time issue, I'm just going to present the one from 2017 August to 2018 August, so 1 year, with the ADCP and the CT data available. We're going to test the open boundary scheme with the river to the east, and we're going to test the daily southwest temperature salinity fields, which were saved every 24 hours at 0 o'clock UTC time. So there's no tidal variation, unfortunately, but we're going to see how the relocatable model works. Before I show you the model results, the one important automatic step is the coastline improvement. So I'm showing two panels here. The left one is before applying the grid tool. The right panel is after. So as you can see, the holes are filled up and the channels have been corrected, which is important. So first, let's look at the tidal elevation in the Bligh Island area. So that's the two panels. The upper one is the amplitude. The lower one is the phase comparison. The blue color line is the model results. The red one is the observation. So as you can see, for the major tidal constituents listed in the horizontal, they pretty much well. In the complex plan, most of them are pretty minor, except the M2, which has the largest amplitude, with like a 12 centimeter error here, which can be improved in the future. Now we look at the ADCP comparison in the Cook Channel. So the top two panels are ADCP data. The left one is the U component. The right one is the V component. The U is pretty minor compared with V because this is a channel. The bottom two panels are model results. As you can see, the model can reproduce the strong, not only the tidal signal, but also the non-tidal current. The right panel here is the error bar. So for the most depths, the error for V is less than 8 centimeters. Another important part is the temperature and salinity comparison. We have 4 panels here, top 2 from the subsurface ADCP, the bottom 2 for near bottom comparison. The left 2 panels are temperature, right 2 panels salinity. There are 3 different colors. The red one is the CTD data. The blue one is the relocatable model results. The green one is the Southwest, the parent model results, which doesn't have the the tidal spikes because it's only daily data. So as you can see, the model actually can generate the certain tidal elevation as the tidal spikes here. The most improvement is actually for the near bottom. For both temperature and salinity, as you can see, the blue color line is closer to the red lines and show a better variation. If we look at the numbers here, the error bar for the relocatable model actually can be half or even less for the temperature and salinity near bottom. Second case study is for the Prince Rupert area. We tested the one-way nested model, so we have 2 levels of the nested grid. The first one It's about a 300 meter resolution in horizontal. The level 2, which is on the bottom panel, has a 60 meter resolution. Both have 120 vertical layers, Z levels. And we're going to use the level 1 model for the tidal comparison at the Prince Rupert. Use the level 2 nested model for the ADCP and the CT data comparison. So this is tidal elevation comparison again. We have 5 major tidal constituents listed here. The top one is the amplitude comparison. The bottom one is the phase comparison. The red one is the observation. The blue dashed line for model results. In the complex plan, they're pretty reasonable, but there's a space that we could improve later. Maybe I'm going to cover that later. So for the ADCP comparison, of the in this deeper channel here, about 120 meter deep, the top 2 are U and V components from ADCP, the bottom 2 from model level 2. The model actually not only can reproduce the currents, but also the vertical structure. As you can see here, we have a strong baroclinic tides near bottom part. The error bar can go as a minimum as 4 centimeters. So it's a reasonable performance. And for the subsurface at the near bottom CDD comparison, again, top 2 panels for subsurface, bottom 2 for near bottom, temperature on the left, salinity on the right. There's 3 colored lines again. The blue one is the model, the green one is the Southwest, the red one is the CDD data. So the model, so not much story for salinity, but for the temperature, in the summertime, because it's well stratified, the tidal spikes is pretty clear. And the late fall, it's well mixed for the subsurface. For the near bottom, again, we see the significant improvement because I think it's because of the vertical resolution in the relocatable model. We can see the model can generate a better, more realistic variation for the bottom temperature. So summarize this study. This is a relocatable model for the West Coast Canada. It's for planning and demonstration purpose. We tested the parent models, which can provide a good initial condition and open boundary condition. We tested referential models from OPPFA 1 and 2 for parameters and the configuration. We also tested all the tools here. They work pretty well for this automatic system. So it can be set up quickly and generate reasonable results based on the data comparison for both the tides, ADCP, and the CDD. In the future, we hope we can develop the version 1 on the OPP and improve the model performance, such as the tides I mentioned before, to introduce external tidal database. And final slide, I think for a few thoughts here about the potential use of this quick automatic system. It's really, I mean, once it's developed, there's almost no cost to run the model. You can change your domain resolution quickly and test it. So I think it's not only good for emergency response use, you can also use it for pre-study for a more advanced numerical study later. So such as how to select a domain, how to understand the basic oceanography and do the pre-feed engineering study design as well. If this region there's no good model and no data in the history, it would be a good way to use this technique to design or plan observational plan, like where to put the ADCP. And it can also be used as a dynamic interpolation from the coast like 2.5 kilometer southwest or Alps model results to provide a finer, high resolution in both the time and the space. So you can save like even every 5 minutes. So Thank you for listening. And if you have any question and comments, I appreciate that. Thank you.
Thank you again for another very interesting presentation. We have at least a couple of questions. We'll start with the first one. Sorry. Shumin, would you like to ask your question?
Oh, yes. Hi, thank you, Andy. Thank you for your talk. I'm just kind of curious about the tidal constituent in Prince Rupert, and you just show that S2 is much stronger than K1 over there. And I'm kind of curious why S2 is particularly stronger in Prince Rupert. Do you know why?
Why particularly K1 is stronger?
This one, S2 is stronger than K1 from the amplitude. And in the first case, K1 is stronger. So I'm kind of wondering why that's different.
Oh, yeah, that's a good question. I'm going to look at these details because this is not particular design for study the tides in the Prince Rupert area. We just selected Prince Rupert because it's a further inland area. With very large tides as like 2 meters, but we were focusing on the M2, unfortunately. So, but it's a good question. We can do more research on this later.
Yeah, cool. Thank you.
Susan, a planning question for the session. I'm wondering if the 10-minute additional gap between Talk 3 and Talk 4 is because we have no posters in this subsession.
Oh, yes, that could be it.
Because that's what happened in the morning. We had the 3 talks, 2 posters, 3 talks. And I'm wondering if CMOS has generically left that. Because I'm just wondering, do we go ahead or do we get ourselves off timing with other sessions?
Well, I would say that we're going to make Andy at least answer a flotilla of questions before we move on.
Okay, because there's a lot of questions for Andy in the chat, so let's keep going then, and we'll go on the scheduled timing slots. So the next question for Andy is from Laura.
Hi, Andy. Thanks for the great talk. So I just was wondering, what are you doing for the river forcing in your relocatable model? Do you have like a database and that have access to, or do you have access to a hydrological model? What if your new region has rivers and you don't have data for them? So how do you deal with that?
Yeah, you just go directly to the most challenging part, particularly for NEMO 3.6 here, because it doesn't have wet and drying function. We hope, with maybe upgrade to NEMO 4.2, or then we could have based on the database of the bathymetry, we can extend our domain to the river. Another challenge is not the technique, is the availability of a river database. So we don't have, even for gorge, the major rivers, we don't have such a good thing. If anything, we can grab from parent model, such as SALP, we can use it. But I don't think even for SALP, rivers we are using climatology rivers discharge, I think. So it's definitely.
I was hoping you had found something that I wasn't aware of.
No, but this work, I have to say, because it only start from last September. We do what we can do within the time scale here. So, but that's the one of the challenging part. Since I have time, as I heard. You can see the list of the further areas for the development, river database, and the tools. So hopefully we can extend it. But with the nested domain, it's going to help us. So we can use a big domain, cover the river mouth, then go straight to a nested domain for your study area. I think that's the way to go. But definitely we need a river database.
Before we go into the next question, I'm just going to make a comment / advertisement. Next week, there's going to be a talk here at CMOS by one of my grad students Teo Weiss-Gibbons, who's going to be talking about the forcing NEMO with the output of a hydrological model that represents a large number of rivers around the Arctic and Canada, and how that changes compared to some of the databases. So I think the river question, how to do the runoff, is really important. So given that was a little side, I took advantage of being co-coordinator. I think our next question is from Christoph.
Yeah, nice talk, Andy. I was just wondering, so your coastline is pretty complex and the bathymetry is quite shallow. So I can imagine there to be lots of nonlinear interactions to take place. And I know from my own NEMO configurations that the lack of the wetting and drying has led to some problems in the mean circulation. So I was wondering if you had validated or looked into how well nonlinearities in the models are represented, for example, by validating not just the mean tidal constituents, but also overtides, like M4, for example.
Again, yeah, that's a good question. Not much time to go that further, not far yet. Yeah, but for the nonlinear issue, particularly, maybe go back a little bit for Laura's question. The river we can test is only through the open boundary condition. We can actually try different open boundary schemes. But another thing, good thing is as I say, any internal tides or barokinetic tides, we can got that. But for your question, we definitely need a further effort to examine.
Okay, thanks.
The next question is from Jin Yu.
Hi, Andy. So I have a question. You showed a comparison between simulated and observed temperature. And occasionally there are some larger differences, or any physical explanation for larger differences?
Yeah, I think you mean this one, because this is a...
You need to share your screen. You need to share your screen. Oh, maybe you don't. No matter, you did. Yeah,
it is shared, yes.
Yeah, you did. So just look at the near bottom, for example. Which one is observed? I saw this as the CTD is red, isn't it?
Yeah, the red one is observation.
Right. So now you occasionally see the deviation, the blue color from the red.
Yeah.
Right. And any particular reason for such larger differences occasionally?
Yeah, I think that first it's clear there's kind of like a time lag. That's one part. But I understand that the relocatable model, what it can do, because of all the open boundary actually using the daily temperature as open boundary from the south, from the parent model. So it actually has to resist that open boundary condition. How to say that? If it's a pure prognostic, I think this one could be better. This comparison could be better. If I extend the relocatable domain to further, so let the model interior area generate its pure prognostic temperature, I think that's going to improve it. But here, the open boundary condition is the issue to constrain.
But it could be also with the negative flux and the water mix, because it's this is
for the near bottom part, for the near bottom part, I think it's less, but for the surface one, I find because we are using the HRTPS, which is a 2 kilometer, 2.5 kilometer resolution. So for the further inland area, it's going to be challenging to get the heat flux correct. So I found that for the subsurface one, actually, the discrepancy here is maybe from the overheat of the surface layer. But all those need to find. I want to make a statement here. This is a relocatable model. It's you just select a domain, set up the resolution, and it can go. So we kind of trade for the performance to the speed or to the responding time. If we have more time, we definitely can. As I said, this one can be a pre-study. Right? We can go more advanced. To dig out what really going on and what we can improve the relocatable model.
Thank you, Andy.
Thank you. Yeah, we
Very
can
good. Thanks,
discuss
Andy,
it.
for answering all those extra questions. So that was great. Thank you very much. But I think it's perfect
To
timing.
my,
to
yeah,
talk
to my
about next
hotspot spotlight for me. Yeah, thank you.
Yes, thank you, Andy. Our next talk is by Michael Dunphy, and he's going to talk on port modeling on the West Coast under the Oceans Protection Plan. Go ahead, Michael.
All right, thank you, Susan. Is slides coming through?
Yes, looks
Yes.
good.
Okay, great. All right, so thanks everyone. Today I'm going to talk about the port modeling on the West Coast that we've been doing under the Oceans Protection Plan. And this is mostly done by myself with Maxime and Hauke at iOS in Sydney. We also have contributions from the DFO OPP modeling group here and our colleagues at Environment Canada. So what we've done is we've developed 6 high-resolution port models under Ocean Protection Plan. They're all based on NEMO 3.6. We have 3 on the West Coast, 3 on the East Coast. The purpose of the models is to address 2 needs. One of them is to enhance electronic navigation by providing water level and surface current forecasts to the people that drive the ships, and also to provide ocean conditions for incident response, spill, search and rescue, that kind of thing. So the models will be operationalized at Environment Canada. I don't have the time scale for that right now, but it's pending. And they will run in the sort of real-time catch-up once per day, plus 4 forecasts. So every 6 hours will be a new forecast. So today I'll just give a quick overview of the models and a bit of evaluation. So, so the West Coast models, we've got Kitimat at 500 and 100 meters, and this development has been led by Hauke Blanken. That's the north model. We also have at the south, Fraser River 30 meters and Vancouver Harbor 20 meters, and those worked on by myself and Maxime. The larger, we get boundary conditions from the larger scale models. This is CMOS West, which is a 2 to 2.5 kilometer Northeast Pacific model. It's been talked about in lots of different contexts. Version 2 has been operational since December. We also have the Salish C500 model, which is Susan Allen's model. It's been tech transferred to DFO from UBC, and it's been in experimental operation since December. So that's the large red square here, and then I'll be focusing more on these smaller boxes over there, and I have a better graphic coming up. So I'll start with Kitimat at the north. So we have an outer domain at 500 meters here, which reaches into Hecate Strait and covers the Douglas Channel Kitimat area, 50 levels for that. And then the inner domain, which is this dashed area, is sort of the approach to the port. That's where we have 100 meters resolution. The boundary conditions come from CMOS West at the boundary. It's one-way offline forcing. So CMOS runs, saves output. We use that to force the 500 meter. We save the output, run the 100 meter. And that's the same for all the ports. Tides come from web tide, surface forcing from HRDPS, and we have a combination of real rivers, gauged rivers and climatological rivers to input all the runoff here. Similarly for temperature, some climatology and some measured. And we have a 6-year hindcast conducted from January 1st, 2016 to 2022 here. And we'll do a little bit of evaluation the next couple of slides. So quick look at the M2 tide. We have 3 tide stations here, 3 water level stations. Observations in black, model in 500 meter model in green, and for reference, the COPS model is in red. And I've got amplitude phase here on the top, and the bottom is difference from observations. So in both cases, we're doing a little better on the M2 amplitude and phase. Jumping to the next slide, we see a similar picture on the S2 tide. You know, we're doing a little better on both amplitude and phase. going through all the tidal constituents, I'll jump to sea surface temperature. So we have one sea surface temperature buoy here. Again, black is observations. The CMOS model for reference is in blue, and the Kitimat model is in red at 500 meters, green at 100 meters. And we're clearly capturing the seasonal cycle here of sea surface temperature. And we can see that CMOS is definitely underestimating the temperature in the summer here. So part of that is due to resolution, but part of that's just due to the better river forcing. Let's see surface temperature, and then a quick look at CTD profiles for water properties. To my eye, these are doing about the same in terms of quality. We may that cold bias at the surface is kind of switched into a small warm bias now, but in terms of depth profile, we're about the same. Okay, so that's a quick look at Kitimat. Then the next model is the Vancouver Harbour Fraser River model. So the way we've set this up is we have an outer domain at 125 meters. I call this the South Salish Sea domain. It covers Pitt Lake over here. It covers Howe Sound, Vancouver Harbour, Indian Arm, and the Fraser River up to Mission. The open boundaries. Okay, so, and then within this domain, we have a 20-meter zoom for Vancouver Harbour, which is this square box or rectangular box. And then similarly for the Fraser River, we have a 30-meter zoom here. And these are sort of targeted to where the bulk of the shipping traffic is. So that's why the extents are where they are. The south and west boundaries here come from the Salish Sea 500 model that's in experimental operations I mentioned before. Then the other boundary is this open boundary at Mission. This has a sea surface height boundary condition, which we force by Mission water level. And for forecast, we have a non-stationary tide model to project the Mission water level into the future for the 48-hour forecasts. We also have freshwater input from North Vancouver rivers like the Capilano and the Seymour. We also have climatological input at Howe Sound, Indian Arm, and Pitt Lake. The one consequence of doing this sea surface boundary condition here is that the discharge through the Fraser is implicit, so we have to control the bottom friction carefully to get that right. So it's a tuning process that we've done. Again, surface forcing HRDPS, we have a 5-year hindcast here. So couple words on the non-stationary model. So the non-stationary model, it's much like T-tide, but it takes into account non-stationary tides. Here I have Mission gauge in blue. I have the prediction from the non-stationary model in orange, and then the difference in green. So it captures well the freshet here. Whoops. And down below, I can separate the orange part, this non-stationary prediction, into a stage part in purple and a tidal part in red. So what happens is during the winter, when you have low flow season, you have pretty strong tides here, maybe 1 to 2 meters. But as the freshet ramps up, the tides get wiped out. They just can't propagate up to Mission anymore. And then as the freshet declines, the tides recover. So we're using this for the forecast part. So I won't spend too much time on that and just jump to some evaluation results now. So a quick look at tidal error in Vancouver. So we have 12 forced constituents, and for these 12, our tidal error is below 1 centimeter for each. So they're in pretty good shape. Well, at or below 1 centimeter. I guess one of them here is 1 centimeter. Jumping to total water level across the domain. I'm comparing here Salish Sea 500 on the left and our 125-meter model on the right. We have kind of a consistent 11 to 12 centimeter error in terms of centered RMSE. And total water level error is doing better than Salish Sea at the Fraser River stations, because the Fraser River in Salish 500 is fairly crude. So we're doing significantly better there. And what's interesting is within the river and without the river, in river stations and out river stations are not substantially different. We're all kind of in this 12 centimeter range. It's a fairly harsh error measure, I believe, because it includes any mismatch in the forced constituents. I showed those on the previous slide. They're very small. but we also have mismatches in shallow water and overtides that I'm not showing here. Constituents that are just not forced, those contribute to the error, and plus, of course, the surge error. So in the interest of time, I won't spend more time on that, but this is sort of a summary of how we're doing, 12 centimeters RMSE. And only showing the 125 meter model because the 20 and 30 meter zooms inherit the same water levels to a very good approximation. So they're not substantially different from this. Quick look at sea surface temperature in English Bay. We capture the seasonal cycle. It's about the same as Salish C500 as in our zoom domain. If we look at CTDs in the part outside of the river and outside of Vancouver Harbor, where the mouth of the Fraser dumps out into the plume area, if you will, we're doing pretty comparable to Salish 500, but we might be doing a little better in salinity. And this is likely due to better resolution and or better river forcing. So that's that. And then at Woodward's Landing, we have a horizontal ADCP that measures the flow. This is in the near the mouth of the Fraser River. Positive is upstream, negative is downstream. So the observed in blue and the 30 meter model in orange, and we're capturing quite well the outflow, the mean outflow, which is approximately 1 knot, with the mean level here. And we're also capturing the range quite well, which is approximately 4 knots peak to peak. So it's working pretty well. Similarly, in Vancouver Harbor, we have another HADCP at Second Narrows. If you're familiar with the area, then you know where that is. And again, observed is in blue and our model is in orange, and we're capturing pretty well. The green curve is a prediction based entirely on CHS constituents that they use for a prediction. And to my eye, I think we're doing a little better than constituents in some cases. And yeah, and again, we're capturing the range. The mean flow here is quite small. All right, so that takes me to the summary slide. So high resolution real-time forecast models for Kitimat, Lower Fraser River, Vancouver Harbor have been developed. They're running daily in a sort of best effort mode in user accounts. Experimental operations and operations will follow. Model performance is good. We're working through the process of doing up a formal report on the performance. And looking forward, or looking to the future for improvements for version 2, right? So we have version 1, version 2 will be better, version 3 will be even better. Things on the short list are upgraded Nemo 2, trying to use the wet and dry feature, which is probably more relevant for the Vancouver Harbor Fraser River area than Kitimat. We can look into using AGRIF so that we can run these in 1 or 2-way online nesting instead of offline nesting. Also, we can get some additional forcing, have a look at the other tidal constituents, and increase the resolution as our compute capacity permits. So if you're interested in the models, please contact me. It occurs to me there must be a lot of interesting things to do with them. One of these things might be hooking it up to Susan's BioGeo model to see how that works in Vancouver Harbor, because that part's not in Salish 500. And please see the next talk from Rachel, who's going to talk about our East Coast ports. So I think I'm kind of on time, so that's it. Do I have questions?
Great, thank you very much for another interesting presentation. Yeah, we have a perfect timing. Question disappeared. Shubin, would you like to ask it, please?
Oh, hi, Michael. Yeah, I'm just super curious that can I get the hourly river flow rate or river flux from your model as a Fraser River?
You'd like to get it? Yeah, just pop me a message and then I can save that. Yeah.
Yeah, awesome. Thank you.
Okay.
Andy, no, sorry, that's another discussion. I'm going to throw a question in. As you start to get down, you know, with 200 meters, and you even talked about, you know, tens of meters, are there any issues with how, you know, Nemo's setup that is, you know, because you're starting to look at some very different scale processes that people were running it in, you know, regional models, quarter degree or that. Do you notice, you know, do you notice any potential issues or, you know, things that that really needs to be thought about is with getting to those scales compared to the much larger sort of regional global scales?
One thing that stands out is that we're still a hydrostatic model. So if there's anything non-hydrostatic going on, we'd be capturing just like a hydrostatic approximation of it. Aside from that, the model actually seems to perform reasonably well. I've not run into any other scale things yet, but that may change as we continue to dig into it. I think the lack of the wetting and drying is sort of a key gap at the moment. And that should make a big difference once we put that in.
Great, thank you. Maybe we've time for one last question, Jinyu.
Yeah, nice talk. So my question is, your circulation model has a really good performance, but I'm wondering whether in your future work you should include the effect of the surface wave, particularly the effect of the surface wave on the bottom mixing, radiation stress, and bottom strike, etc., to your circulation model to get even better performance.
Yeah, that would fall under further tuning and further improvements. I don't know that that's a leading order issue at the moment, though.
Well, in the coastal water, maybe, you know what I mean? So you could have a big surface wave and stir the whole water column.
Yeah, that's right.
You know what I mean? And particularly wave breaking, you could generate additional sea level change and currents.
Yeah, so I guess the way to achieve that would be a coupled wave model.
Yeah, that's what I'm trying to suggest.
Okay. Yeah, that would.
Okay.
Our waves are a lot smaller than yours, Jinyu. An awful lot smaller.
I see. Okay. All right.
Thank you again, and thanks for the questions. On to the next speaker.
The next speaker is Rachel Horwitz, who's going to give a talk very similar to the last one with one word change: port modeling on the East Coast under the Ocean Protection Plan. Take it away, Rachel.
Hi, yep. Let me just share my screen. All right. Yep, thanks. This is very much the second half of the talk that Michael gave, but we've got 6 ports, so we decided we could get a few extra minutes to talk about each one. So this list of contributors is the same as Michael's, just flip top to bottom here. So yeah, I'm Rachel, and the models I'm going to talk about were almost entirely developed by Stephanie, Adam, and Simone, and I'm here sort of representing the East Coast cohort. So yeah, same background. I'm gonna skip this because Michael just covered it, but we're now going to look at the East Coast 3 models that were also developed under the Oceans Protection Plan. So the 3 areas today are the St. Lawrence Estuary, the St. John Harbor and the Bay of Fundy, and Canto Strait. And we don't have Susan's mid-size model between these domains and CEOPS, so the outer boundaries are all forced by the East Coast half of Environment Canada's newest CEOPS model. So first, for the St. Lawrence, there's a 500-meter domain and a 200-meter inner domain that's also set quite a bit upriver in order to have a better connection to the 1D river model that forces it. And there, the tides can propagate up the river and the runoff flows out. The model also includes a fjord that has, I guess, some industrial areas of interest. And sort of a point to note is this is the only one of our 6 port models that has a lot of sea ice. We're not directly modeling it, but take the ice from the CEOPS parent model and use NEMO's ice if condition for the thermodynamics. And the St. Lawrence also has a notable hydraulic slope. So in addition to looking at the tidal elevation for the tides, and this is the M2 amplitudes running up, the upriver is to the left here, and then downriver plus the fjord for the right 2 stations shown in these figures. So we get the M2 amplitude decreasing as you go upriver, as well as the phase lagging following the observations. Here the observations are black. We also have a hydraulic slope that obviously decreases going out to sea. And part of the reason the inner model domain has that sort of far western boundary is because the 500-meter grid and the CEOPS forcing model both have too high of a hydraulic slope, in some areas of interest. And so that boundary was pulled back to get the correct hydraulic slope and therefore the correct mean flow out of the estuary. We were able to put some horizontal ADCPs in the estuary between Quebec and Lévis. Each one extends just about 150 meters from shore, so that does put us in our nearest to shore or second nearest to shore grid cells. So if we compare the along channel currents from each ADCPs with the model here, we have the observations in blue, the higher resolution model is in red, and the coarser resolution model is in green. So we do get the amplitude and phase fairly well, but it seems like on the Lévis side, we're underestimating the currents a bit. On the Quebec side, we're overestimating the currents a bit. So it's a bit of a open question, point of investigation as to whether it's just that we really can't resolve the bathymetry well enough. In the 200-meter model, it's still only 7-ish grid cells across, so maybe we have no chance of getting that horizontal distribution right, or if it has something to do with the friction of the lateral boundaries. So that's something Simone is continuing to look at. There's also a ferry that runs from St. Lawrence all the way out to Newfoundland periodically, and that has a temperature and salinity sensor on it. And so that's one place we've been able to look to see the great improvement that these models have been able to do over the parent or the larger forcing model. So the observations are on the left. So it's about a year here from January at the bottom, time going up, and then the finer resolution, coarser resolution model and the CMOS model on the far right. So we can see both these models do a much better job at capturing the salinity in this figure than CMOS, which is far too fresh and far too well mixed, which you can see in the C to D profiles examples on the right. And so this has taken some tuning to make the salinity and the baroclinic structure correct in the inner models when it's being forced at the boundary by a model that does not capture that. The second port is the Strait of Canso, so that's between the mainland of Nova Scotia and Cape Breton Island. And Canso has very small tides and no major freshwater input, so it's a little different than the other ports because it's really the North Atlantic Ocean coming right into the strait, and the main reason for needing this nesting is to get down to resolve the complex bathymetry in the area. So there is a strait and an island and a sill that the larger CMOS model run by Environment Canada doesn't capture. The tides are relatively small here, but they are captured very well. There's a bunch of ADCPs that were deployed and a tide gauge. So in the vertical, we're within 0.5 centimeter of the M2 amplitude, and also for the current, so the tide gauge is usually within 1 centimeter per second root mean square error and within a degree or a few degrees of phase. Here is one site where the non-tidal currents are actually larger than the tidal current, so we want to make sure to look at that. And here the observations are in red and our two models are in blue, with the larger forcing model in green. So we're definitely capturing these sort of synoptic scale current variations that are the largest contribution to the current, much better than the larger outer model, which I think it doesn't have the sill that's at the mouth of this strait. So it really is not able to capture the sort of weather time scale currents. There's also a buoy in this inner model domain we can take a look at to see sea surface temperature. So we're doing a good job capturing the seasonal cycle and also the change in variability with the seasons. There is some seasonal cycle to the error, certainly larger in the summer than the winter, but overall the mean bias is 1/10 of a degree, so that's very good. And I think because the temperature is and salinity water properties are forced so much by the outer domain, the CMOS model, it may be difficult to improve on this in the inner domains. And I guess Adam wanted to point out that with this buoys like this that are real-time data, it has a potential for a sort of this is not real-time data validation, but moving forward in forecasts, that's something that would be possible. He's also taken a look at some of the sort of dynamics of this saltwater renewal behind the sill. So here there's ADCP data and currents from his 100-meter resolution model, showing they capture this larger positive flow, and that corresponds to flow over this sill. And at the same time, you can see that there's a big jump in salinity in a fairly short time period. So 1.5 PSU increase in salinity. And in these models, that salinity goes up and stays high, while in the larger forcing model, it does have the spike in salinity, but the saltwater flows right back out because it's, again, missing the bathymetry resolution to have a sill that will hold the salt water behind it once the gravity current takes it over. And the last region I'll talk about is the Bay of Fundy and St. John Harbor models. Bay of Fundy, of course, is known for very, very large tides. And in the harbor, there's an 8-meter tidal range. There's also a fairly large river, St. John River, up to 5,000 cubic meters per second. And in the harbor, there's complex man-made bathymetry with some seawalls and dredge channels. So the water level simulation is going very well. The tide gauge M2 amplitude is very close to both of the models, less than a centimeter error, and the phases are very close. Both are an improvement over web tide, which is what's usually used in the area for tidal constituents. Here, the tidal elevations are much larger than the non-tidal ones, but if we look at the non-tidal water levels, we can also see we're capturing the sort of larger wintertime variability and synoptic scale variation throughout the year. We were able to put some ADCPs in the water and can also take a look at the tidal currents, which here are just the five major constituents, but doing very well at the amplitude and the phase and the angle of the ellipses here in the harbor. The tides do make leaving moorings and CTDs in the harbor quite difficult. So in addition to using our own data that we've collected, we're sort of looked around and found the Coastal Environmental Baseline Program to also provide us with some temperature and salinity data. So here's an example of a temperature time series from about 2 months from the mouth of the Musquash Estuary, which is just down the coast from the harbor. And this was an area that was not particularly a focus of model development at all, because the focus has really been in the industrial port. So it was really nice to see that we're capturing both the sort of tidal and weekly variation in the temperature somewhere else in our model domain as well. Because all the models that we've talked about, that Michael talked about and I talked about, were version 3.6. Because the St. John and Bay of Fundy models are sort of the first to reach somewhat of a completion with the 3.6 models, it's where we've been able to start developing the next version, NEMO 4 version, that includes wetting and drying, which again, in the Bay of Fundy is probably the most relevant of these ports to have that. So we now have sort of a research version of the model where we can capture the wetting and drying, the extensive mudflats in the Upper Minas Basin, and also in the small bays closer to St. John. And William Zhu has been running the 100-meter version of this model. And then the sort of last thing we've been working on, and what we're hoping to work on moving forward now that the models are somewhat established, is doing some science with them. We did have some drifters deployed for model validation purposes, and noticed one of them actually went into that estuary I just mentioned, which is the Musquash Marine Protected Area. So that gave us some interest into what the connectivity between this industrial port is and the MPA that's just down the coast. So we've started just a few particle tracking type simulations looking at where particles that start anywhere in this domain might end up. So the red ones all start anywhere in the harbor and end up in the estuary after a 2-day advection period. But we can also just see generally that they're aligning at the edge of the river plume, and that's the type of process we'll be looking into more as we have time to use these models as we move into phase 2 of the Oceans Protection Plan. So I guess I'll end there and say that today we showed a summary of, I showed 3 ports and Michael showed the other 3, and they all have 5 or now 6+ year hindcasts available that have been validated in various ways. Environment Canada is going to be taking them into operations, and they are also running forecasts at sort of the research level now before Environment Canada takes them over but we are also continuing to develop and improve them and welcome collaboration. So if you're interested in using any of these model outputs, get in touch with me or Michael, and we'll direct you towards the correct port modeler for that. I will leave with, wrong direction, leave you with just a map of all 6 ports to jog your memory in case you have any questions. Thanks.
Thank you for another really interesting presentation. Susan, we have time for one question. I'll give it to you, Susan.
Thank you, Rachel and Michael. Very exciting talks. Rachel, I think you said, but I just want to make sure you said you have a working research version of NEMO 4 running for one of the ports.
Yeah, so for the Bay of Fundy and St. John Harbor models, we've got the NEMO 4 version going with the wetting and drying. So that's
super exciting.
There we
Who's
go.
the best contact for that? You?
Yeah, that's me. Yeah, I'm right now. I've been running the 500 meter one, and William's been running the 100 meter one. But yeah, they're both running and seem to be running well. I can't seem to stay on that slide and get the movies going again. But yeah.
Okay, thank you.
And we're using NEMO 4.04 because we started developing it before NEMO 4.2 was available.
Yep.
Sorry, may I have your email address again? Sorry.
Yes, there you go.
Thank you.
Great, thank you. And now we should move on to our last speaker of the session.
So our last speaker today is James Monroe, who's going to talk about enabling ocean modeling with CIUS data. Take it away, James.
Good afternoon, everybody. So I'm here representing CIUS this afternoon. CIUS, of course, is an ocean observing consortium across Canada that's been working on trying to get our oceanographic data more accessible. And I want to talk today about how we're going to work towards enable ocean modeling under CIUS. So first of all, in terms of CIUS broadly, CIUS is an example of an OOS, an ocean observing system, and there's many of them around the world. CIUS is sort of coming a little bit late to the game in terms of being set up, but it's taking best practices from several of these OOSes as a way of cataloging and making oceanographic data discoverable for lots of use cases. The theme here in terms of oceanographic data is we've gone from a transition from oceanographic data being scarce, rare, hard to get, to being very, very common, right? You've got automated platforms, you've got robotic systems, you've got remote sensing systems. We've gone from scarce amount of data to almost too much data. And so the challenge goes from being able to get to the data to be able to find the data that you want, trying to discover it. So what we're trying to do within CIUS is enable access to that oceanographic data, which we are collectively collecting, making it available and reducing waste in the system, basically moving things forward for everybody. So the mission of CIUS is to foster a partnership and grow a powerful online platform that generates information, knowledge, and place-based solutions to advance our understanding of the ocean. So we're trying to help everybody move along in terms of help, whether it be academics or industry or government or education, move forward our knowledge of the ocean by leveraging the wonderful work that's being done across this country. Okay, and when we talk about oceanographic data, one of the guiding principles we have is the FAIR principle. So we're thinking about our oceanographic data, and we want to make sure that data is findable, discoverable. You got to know how to get to it. It's not sufficient to have an email address for someone you can just go and contact, like we just heard in the last talk. You want to be able to go somewhere and do search and discover the data that you're looking for. Once you know that the data exists, you got to be able to get to it. It's no good if the data is trapped behind some firewall on some system you don't have access to, or it's not physically accessible because you can't download it because you don't have the bandwidth. If you want to get that data, you want to make sure it's interoperable. Interoperable with both in the format that make it useful for you to use, but also interoperable in the sense that the way that we collect and store and catalog our data is the same process that other OOSes are using. And finally, we want our data to be reusable. data takes a lot of effort to collect. And in fact, with observational data, it's not like you can go back and take the same measurement of the water at the same point in time. Again, you want to be able to reuse that data. So what CMOS is doing is building a Canadian version of trying to enable all of that oceanographic data so we can build new and exciting applications with it. So when we talk about CMOS as an organization is 3-4 years old now at this point in terms of its name and its formal funding. There is no actual, there's a little bit of a CMOS national, but the reality is CMOS is made up of a number of regional associations, CMOS Pacific, CMOS Atlantic, and SLGO in the center. And each one of those has various partner organizations that are part of it. And the way that we've developed CMOS is we're structured around these regional associations. It's the regional associations which are going out, finding data, working with oceanographic, with partners, assessing that data, bringing into catalogs, and making it available. And a lot of the structure of CMOS has been based by talking to other USAs, like the American Integrated Ocean Observing System, and other regional USAs in North America, taking best practices from what they've done. Okay, so up to this point, there's a little history on what CMOS is. CMOS is a way of making oceanographic data available. CMOS itself doesn't necessarily collect data, but we're taking the data that may only exist within one partner and making it available to others. So as a schematic, you can think about what is CMOS. CMOS is taking all of that data, which might be open or slightly open, putting some metadata around it, good descriptions of it so that it can be discovered, putting some web services in front of that, whether or not that be cataloging or ERDAP or some other way of accessing it, when appropriate, providing some hosting of that data, and then making that data available to end users so that when you're searching for data, you could go to CMOS to see what we have across all of Canada in terms of that data, as opposed to each individual researcher having to go to specific individuals to find that data and redoing this step all the way through. Now, in the early days of CMOS, we focused on observational data, primarily point measurements, moorings, buoys, other individual sensors, and things like model data was pushed forward as in, oh, we'll get to that in a later phase. Well, I'm happy to say that we're moving into that third phase. We've developed a new strategic plan within CMOS, and it's got a number of themes, primarily about increasing the total amount of data that we're thinking about and what kinds of data and building new data products. But I want to draw
I think we've just lost the connection with our speaker.
I was wondering if it was me or James. Sorry to hear that it's James.
Let's give him a minute to hopefully reconnect. Anyone have any quick questions for any of the other speakers while we're waiting? With the assumption that if James come back, we'll instantly switch back to his talk.
Maybe I have a quick question about for Michael. Is the model data available on some websites?
The data is not available on a website, but I can transfer some to you as needed.
Yeah, cool. Thanks.
It's all piled up on our internal computers at the moment.
Yeah.
there anyone else here from St. John's, just in case they didn't have a power outage there or something?
I think he's not in St. John's.
Oh, okay. Well, James is at Memorial, so
Yeah, but
he
he's
might
not
have
in
been
St.
there.
John's right now. I think
Okay.
he's not located.
Okay, then then it's just whatever joys of connection.
Yeah, I think he's currently sitting in Ontario.
Paul, you mentioned the 4.2, NEMO 4.2. Is that a global domain?
We are testing it out on the global domain. Yes, we
So
don't
that-
have it running yet, but that is on our. That's what Clark is working on, among other things, is getting it running using EORCA 025 as well as our ANA 4.
Okay.
I see a general question from Rachel. Is anyone else using NEMO 4 with wetting and drying? Well, my first thought is I think you're the only one with NEMO 4 working here yet, so unlikely, but others may be trying. Any comments?
Palm is you here. I think Josh is in the Gulf region in Quebec, in DFO, and have some success in running NEMO 4. I'm not sure about wetting drying yet, but I'm not surprised. Joel has the energy Joel has.
Yeah.
Nicola was running it there. Yeah, I know about that.
So what we're going to about the CMOS talk. So we hope hear you back.
We'll give it a couple more minutes. Otherwise, I guess we'll have to, I think end the session and maybe see if there's another chance to get it scheduled later in the meeting.
Is this the last part of our session, Paul?
It's the last part of our session, but maybe we can get it piggybacked into some other session that's got a free slot next week. I'll check on that if James doesn't reappear in the next minute or two.
Okay.
I would say now with only 3 minutes left, Paul, people are probably going to have to go.
Yeah, and it's probably getting quite late East Coast wise for Friday afternoon.
And of course, I still have like 4 meetings to go. So yeah.
Yeah, exactly. So, okay, I think then, unfortunate we lost James. I don't think there's anything we can do. I think we would. Let's thank all the speakers again for 5.5 really interesting talks. I'm sure it would have been 6 full if we could. And then I will, once I hear, I'll check with the email by James afterwards and see if we can get them rescheduled in another session, in which case it will probably come up in one of the CMOS announcements. Thank you.
Thank all the speakers and all the questions. This session has really got me excited. I just can't wait to get back to working on my model. So thank you, everybody.
Yeah,
in fact, I got an email from James from his cell phone saying complete network failure. So he's not coming back.
So Paul and Susan, I think we should thank them, our colleague from France, and they're way too late now, and they're still in the audience. Okay.
Absolutely.
Yeah.
Thank you so much for coming and talking to us.
Yeah. Thank you, Jill.
Okay, well, I guess it's bye, everyone. And next week, more talks, more great talks. Hope to see everybody next week.
Yeah. Okay. Have a good weekend, everyone. Think of NEMO 4 point whatever or over the weekend.
Wetting and drying. It's coming. It's coming. So Paul.